Okay, so in this video we are going to talk about Lewis structures. So Lewis structures are going to show us how these atoms are connected to each other. And I always like to think about these Lewis structures as sort of like a blueprint, right? These are going to show us how the atoms are all connected to each other, but they're going to show them connected in two dimensions. So it's almost kind of like a two-dimensional sketch of what these molecules look like. A little bit later on, we're actually going to take these Lewis structures and transform them into 3D pictures so that we can see in 3 dimensions what these molecules actually look like. But before we can do that, we need to figure out how these atoms are connected to each other, who's connected to who. Okay, so what we've been talking about so far is the molecular formula, which is going to show us the number and kinds of atoms. So something like CH4. Whoops, good to have my pen set up. Right. So this molecular formula shows us that we have 1 carbon and 4 hydrogens. But this formula doesn't tell us anything about how they're connected to each other. And that's where the structural formula comes in. It's going to show you how these atoms are arranged. So if I were to take a look at the structural formula for CH4, it would show you that carbon is in the middle and that carbon is bonded to 4 hydrogens that are surrounding the carbon. This is where we're going in this particular video, is we're going to talk about the structural formulas, and we're going to talk about how you figure out what that structural formula looks like. Okay, so what we're going to do is we're going to be doing Lewis structures next, and this is going to give us our molecular formulas or structural formulas. And what I've given you here is a set of guidelines to help you figure out what that structure is going to look like. I highly recommend that you follow these guidelines. Do a bunch of practice with these. I find more people make mistakes by trying to jump ahead, like they think, I know exactly what this structural formula looks like, so I'm just going to go ahead and write it out. It really is helpful to follow these guidelines. You're less likely to make mistakes. All right, so the very first thing we're going to want to do is to draw the total, or determine the total number of valence electrons. Now remember that our valence electrons come from the group or the family, right? So if I have an element that's in group 4, it's going to have 4 valence electrons. If I have two of those elements in that compound, then I need to account for that. So I'd have to multiply that by 2. The second thing I want to do is to draw the skeletal structure. That means that I have to figure out what element goes in the middle, and that is usually the one with the smallest subscript. And then I want to surround that central atom with the remaining elements. I then want to connect those surrounding elements to the central atom with bonds. Those are going to be single lines. And each line represents 2 electrons that are then going to be subtracted from the total number of valence electrons. I am then going to place any remaining electron pairs into the structure to complete the octet. And please make sure you keep these electrons paired. I always say the electrons never go anywhere by themselves. They're always going to go with another electron. So they're always paired up. There'll always be 2 of them. And then the last step, and this is where I see people make mistakes, only form multiple bonds if necessary. And this is usually when the central atom does not have a complete octet. Usually. Okay. So to run you through a few examples. One thing I do want to point out, I may have to go back and erase. I just don't have a ton of space on here to write out a bunch of these structures. So just kind of keep that in mind. All right, so the first one that we are going to do is CCl4. So I have 1 carbon and 4 chlorines. The first thing I'm going to do is I'm going to add up all of my valence electrons. Do that in red. So I have one carbon, and each carbon has 4 valence electrons because carbon sits in group 4, right? So that's going to be a total of 4 electrons from the carbon. I have 4 chlorines, and each of my chlorines has 7 electrons. Chlorine sits in 7A, and so they are going to each have 7 electrons. So 7 times 4 gives me 28. And when I add all of those together, I have a total of 32 valence electrons that will be inside of the structure. Something you're going to want to do to make sure that you've got your structure correct is make sure that all of your electrons are in there. So when I'm done with this structure, I should have 32 electrons in that Lewis structure. All right. Next, I have to figure out what element goes in the middle. Well, usually it's the one with the smallest subscript, so in this case it would be carbon. And then I'm going to put my chlorine atoms around the carbon. So I'm going to surround my carbon with chlorine atoms. Next, I need to connect those elements to the central atom with single lines or bonds. Okay, I'm going to fix this one. It doesn't look too good. So my bonds are going in here in green. And remember that each bond represents 2 electrons, so I have used 8 electrons, 2 for each of the bonds. And I'm going to go in and I'm going to subtract them from the total number of valence electrons. So I'm going to subtract my 8 electrons from the bonds, and that is going to give me, let's pick a different color, let's do purple. That's going to give me 24, that's going to give me 24 electrons that are left over that I have to put into my structure. And that takes us to step number 4. I'm going to put these electrons in as pairs. I'm going to put them in as dots, just like we did with Lewis symbols. And remember to keep your electrons paired up. They shouldn't have any electrons by themselves. So my 24 electrons are going to go, and I always say do the surrounding elements first, and then go back in and do the central atom if you have to. So all 24 of my electrons are going to go as dots onto the chlorine. Now at this point, I want to make sure that my octet's satisfied for everything and that I have all 32 electrons in here. So each of my atoms is surrounded by 8 electrons. Right, for the carbon I have 4 bonds. For each chlorine I have 1 bond and 6 lone, these are called lone pairs. You're going to hear me refer to them as lone pairs. There are some things I just can't help but saying. So lone pairs, those dots that are on the chlorines, I have 3 lone pairs, so 6 electrons from those electrons plus a bond gives me 8 electrons for each chlorine. So my octet is satisfied for each of them. And when I go in and I count up all the electrons around that central atom, I have 32 electrons. All right, I'm going to go ahead and do another example. I'm going to do another example on the next page. All right, so I'm going to do another example. This time we are going to do pH 3. So I'm going to go ahead and write out the formula. So pH 3. And we are going to go ahead and we are going to add up the total number of valence electrons first. So phosphorus sits in group 5. So phosphorus has a total of 5 electrons, right? I've only got one phosphorus. I have 3 hydrogens. Hydrogen is in 1A. So each hydrogen has a total of 1 electron. And so the total number of valence electrons in this structure is going to be 8. Okay. Now the next thing I have to do is I have to figure out who my central atom is. I only have one phosphorus, so he is going to go in the middle. And then I'm going to surround my phosphorus with hydrogen. I jumped the gun there. There we go. All right. The next thing I need to do is to connect my phosphorus to my hydrogens. I'm going to do that with a single bond in one line. Remember that each line represents 2 electrons, and so I've used 6 lines, 3 lines. 3 lines. 3 times 2 gives me 6, so I've used 6 electrons. And so I have 2 left that have to go into my structure. I cannot, normally I would tell you, put the extra electrons on the outside atoms first. In this case, I cannot. Hydrogen is an exception to the octet rule. Hydrogen only takes 2 electrons. That is it. Once it forms one bond, it is done. It cannot take any more electrons. So my octet for a hydrogen for all 3 of them right now is satisfied. So the only place that I can put my extra electrons is on the phosphorus. So again here I want to double check and make sure that the octet is satisfied for everything and that I've used all 8 electrons in the structure. Well, remember, hydrogen's good when it has 2 electrons, so one bond gives it those 2 electrons, and my phosphorus needs 8, and I have 8 electrons around the phosphorus, 2 from the lone pair up here, and then 6 from each of, or 2 from each of the bonds, giving me 6 plus the 2 from the lone pair. I have a total of 8 electrons, and I've used all 8, so this structure is done. All right, so here in this example, we're going to do carbon dioxide. And this is a great example of when you are going to need to use multiple bonds. So I'll show you exactly how to identify that. All right, so the first thing I'm going to do is to count up all of my valence electrons. Carbon sits in group 4A. So carbon has a total of 4 valence electrons. And I have 2 oxygens, and each of those oxygens is going to contribute 6 electrons. Oxygen sits in 6A. And so from the oxygens, I have 12 electrons. I'm going to add those together, and that gives me 16 total electrons that will be inside the structure. All right, the next thing I have to do is to figure out what atom goes in the middle. Since I only have 1 carbon, I'm going to put carbon in the middle and put each of my oxygens surrounding the carbon. And then I want to go ahead and I connect my carbon to my oxygens. Remember that the single bonds use 2 electrons. I've put 2 single bonds in there, so I have used 4 electrons, which means that I have 12 electrons left to go into the structure. Now, here's where I see people make mistakes. My recommendation is that you take those extra electrons and always put them on the outside atoms first, and then if you have any left over, put them on that middle atom. So I'm going to take these 12 electrons and I'm going to put them on my oxygens. Okay. Once I have done that, now Now I've used up all my electrons. I have 16 in here. And I need to check to make sure the octet is satisfied for every atom in this structure. For oxygen, for both of them, they both have a total of 8 electrons. However, my carbon only has 4. So I need to move things around so that the octet is satisfied. And that is exactly when I want to form multiple bonds. To form multiple bonds, I am going to take a pair of electrons from my oxygen and I'm going to move it to create a double bond. So I'm going to take a pair of electrons from my oxygen and move it to create a double bond. I'm going to do the exact same thing on the other side. All right, I'm going to move a pair of electrons to form a double bond. Now, you may have asked, well, couldn't I have taken 2 pairs of electrons from one atom, from one oxygen, and made a triple bond and then a single bond? In general, you want to make your molecule look as balanced as possible. And it is much more balanced to have a double bond on both sides of that carbon than to have it be a little skewed, right, with a triple bond and a single bond. So this is the structure for carbon dioxide. That is it right there. Again, like I say with everything, make sure you practice. There's lots of examples in the guided practice for you to work with. So now we're going to talk about what to do if you are given a polyatomic ion. You want to follow all the steps that you were given previously, but there are 2 additional things that you are going to do. So when you are accounting for the total number of valence electrons, if it is a negative ion, you are going to add electrons equal to the charge. If it is a positive ion, you are going to subtract electrons equal to the charge. And then the last thing that you're going to do is to place the final structure in brackets with the charge outside as a superscript. All right, so we'll do ammonium as our example. Why do I keep doing that, huh? Okay, so we're going to follow the same rules, right? We're going to count up our total number of valence electrons first. And so for nitrogen, nitrogen sits in group 5, so nitrogen will have 5 electrons. I have 4 hydrogens. Each of them is going to contribute 1 electron since they sit in 1A. And now I'm going to add my charge, right? So my charge here is a +1. And it says that if it's a positive ion, I'm going to subtract electrons equal to the charge. So I'm just going to write a reminder here that I'm dealing with the charge. And I am going to subtract 1 electron since my ion has a +1 charge. And so that means that I have 8 electrons that I'm going to be dealing with inside my structure. Alright, so I'm going to put nitrogen in the middle since I only have 1 of those. And I'm going to surround my nitrogen with my hydrogens. I have 4 of them. And then I'm going to connect my hydrogens to my nitrogen using single bonds. Now I have used 4 bonds. Remember, each bond is 2 electrons, so 4 times 2 is 8. So I have used 8 electrons. So I have 0 electrons left to put into the structure, and this happens sometimes. The last piece for me is to put this whole structure in brackets, and then to place the charge as a superscript outside of the brackets. And that is how you do the Lewis structure for a polyatomic ion. Okay, the last topic is something that's a little bit strange. This is something known as resonance. This is when you have two or more Lewis structures that can be written for one molecule with at least one double bond and one single bond. You are going to see this a lot if you move on to 1211. A lot of the organic molecules, I shouldn't say a lot, but several of the organic molecules that you'll be talking about and dealing with have resonance. And so it's kind of a nice idea to introduce those molecules so that you kind of get a feel for what they look like. Okay, so the example that we are going to use, so the molecule we're going to talk about is ozone. Ozone is that interesting smell when lightning strikes. You kind of get that funny smell. Definitely when there's a thunderstorm nearby, that's ozone. It also provides that protective layer in the atmosphere. It absorbs ultraviolet radiation, so it prevents all of the ultraviolet radiation from coming down to the surface of the Earth. All right. So to do the Lewis structure for ozone, right, I have 3 oxygens. Each of them have 6 electrons. And so inside of this structure, I'm going to have 18 electrons. The only way that I can connect all of these oxygens to each other, right, is to put 1 oxygen in the middle and then I have 2 on either side. And I'm going to connect them to each other with a line. And so here, that is going to use 4 electrons, which is going to give me 14 electrons left over. Those 14 electrons that are left over have to go into my structure. And again, I always say put those extra electrons on the outside atoms first and then go back and put them on the inside atom. So I'm going to do 2, 4, 6, 8, 10, 12, and then the last 2 to make it to 14 are going to go on that atom right there, central oxygen. Okay. So I have put all 18 electrons in this structure. The octet is satisfied for the oxygens on the ends, but the oxygen in the middle is not satisfied. So remember what we did with the carbon dioxide. I am going to take a pair of electrons and I am going to move them to make a double bond. Now, if I do that, oxygen number 1 here has a full octet. Oxygen number 2 also has a full octet. And oxygen number 3 also has a full octet. We're done. But could I have taken and moved that double bond to the other side? Well, let's take a look at that. Let's set everything up over here exactly the same as we had over here. Okay, so I'm going to put all my lone pairs in. And I am still going to label these as oxygen number 1, oxygen number 2, and oxygen number 3. I easily could have taken a pair of electrons from oxygen number 3 and moved them and created a double bond between oxygen 2 and oxygen 3. So this is an example of resonance where I have 2 structures that look, I mean, really honestly, the only thing that's different about them is the placement of that double bond. So this molecule has resonance. The weird and interesting thing about this, and this is something to just tuck away for 1211, is that when we actually take a look at this molecule, we can tell that it's not really a double bond, and it's not really a single bond, but it's actually a hybrid of these two Lewis structures. We'll be talking about that a little bit more later.